A pebble is dropped into a calm pond, causing ripples in the form of concentric circles, as shown below. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? Okay, so I want to kind of look at something real quick on Desmos to think about what's happening here before we do this problem. So if I go to Desmos here, if I put in a table just like 0, 1, 2, 3, 4, 5, 6, 7. If I have a radius, the radius, it tells me, is changing at a constant rate, right? However, let's see, how do I do this from here? I think I get rid of that. The area is also going to change, but the formula for my area of a circle is pi r squared. So watch what's going to happen. I think I can do this. Pi times x1 squared. Okay, so if I have a radius changing at a constant rate, my radius is 1, 2, 3, 4, 5, 6, and so forth, right? Is my, and let me hit this so we can see, is my area changing at a constant rate? It is not. If I graph this, this looks quadratic, right? Which it should be, because my formula for area is a quadratic function. So while my radius changes at a constant rate, my area is not going to be changing at a constant rate. So if I look at the rate of change of the area at 1 foot, it's not going to be the same as it is at 4 feet, right? So this is a related rates problem, because while those two quantities are going to be related, they're not going to be just the same. So now if I looked at something like radius and diameter, those are more directly related. They'd still be different rates of change, but both of them would be constant for that. But this is going to be different. So if we think about what we're looking at when the radius is 4 feet, at what rate is the total area of the disturbed water changing? So we're trying to find the rate of the area. What variable is that going to be in my problem? It's not going to be r. If it is a rate, then it is not going to be just like a straight variable. It is going to be a d something dt. It's going to be dA dt. So what we're looking for here is dA dt. However, we got to start with the formula that we know for area, right? So formula for area of a circle would be pi r squared. So if we take the derivative of that formula, we would have dA dt. Technically, there's a 1 there. Derivative of a is 1, but you got to multiply it by dA dt. So you can put it there if you want, but it's unnecessary. And then we're going to take the derivative of pi r squared. Remember, pi is just a number, so we don't have to use any special rules here. It's just going to be 2 pi r to the first power. But if I take the derivative of any variable with this with respect to time, I've got to put dr dt right there with it. If it were, so pi is just a number, but r is not. For that, r is a variable. Here, that value is changing over time. Pi is always 3.14159. So the r is where we have to put that dr dt. Whenever we're doing like the dy dx stuff, we're on some of those, like when we had x's, we took the derivative, but we didn't have to put the dy dx with it. that was because we were taking the derivative with respect to x. What we're doing when we do related rate problems is we're taking the derivative, in this case, with respect to time, which is not a variable in the problem. So any variable, which that r is a variable, when you take the derivative of it, it's got to have the dr dt or the dA dt or whatever with it. It is a number, so the pi is like a coefficient, so really what you got is you got like 3.14 r squared, and you're taking the derivative of that, so you're doing like 2 times the 3.14, which is like 6.28 r to the first power. And so, but we want to be more precise than 3.14, so we just use that pi right there. If it didn't have a variable with it, it would go away. But since it's sort of like a coefficient for that r squared. Does that make sense? Okay. All right, so once you get to this point, you usually want to plug numbers into your equation. So we got to figure out what each number represents. They give us 1 and 4. So it says the radius of the outer ripple is increasing at a constant rate. So the radius increasing at a rate of 1 foot per second. What variable is that in this equation? The RDT, because it is a rate, so it's going to be a d. It's going to have the d's, the dt's with it. So this is the RDT right here. That's going to be 1, and then it tells us the radius is 4 feet. So that is the r right here, which is good because that plugs in everything except for that dA dt, which is what we're looking for right there. So we'll have dA dt equals 2 pi times 4 times 1, which is going to give us 8 pi. Okay. If a problem has units in the problem, we want to make sure that we put units with our answer. So what are the units for dA dt? Almost. Again, almost. Feet squared per second. Because area is going to be measured in square feet. Time is measured in seconds. If we had feet per second squared, that would be like an acceleration. It would be like feet per second for that, which would be different. Let me show you something else with units right here, because this is kind of cool. And if you take, you guys have all had chemistry, right? Pretty much everybody's had chemistry. So in chemistry, you do a lot of stuff with the, is it called stoichiometry, like your unit conversion stuff. And so that kind of works out in this problem if you want to put the units in. So that was, we had a 2 pi, and then we had 4 feet. So if I want to, I can put 4 feet right here. Now, a lot of times students don't prefer to do this, so I just want to show you how it works. And then my 1 foot per second went here, so I had 1 foot per second. Right? So if we put all of this over 1, you can include the units in the problem whenever you're doing it. And you've got 2 pi times 4 times 1. That is going to give you 8 pi like we got. But look at your units. You got feet times feet, which gives you feet squared. And in the bottom, you just have seconds, so feet squared per second. Okay? And this always works. Like every problem that we do, sometimes it gets complicated. So students don't like to do it. I know when I had physics, our professor would make us put the units in the problem, which gives you one more thing you have to look at. You are not required to do that. You can do it like I did here and just put your units on your answer at the end. But if you include the units in the problem, the units are always going to work out to be the correct units at the end if you treat them like they're a variable and you like square them and do all that with it. So I think that's kind of cool there. I don't usually do that in the problem just because it's more to keep track of, but you can. Now, if we had looked at a different point in time, our area would be changing at a different rate there for that, even though the radius is constant. There. Okay, questions? Okay. All right, here is another one. Okay. Air is being pumped into a spherical balloon at a rate of 4.5 cubic inches per minute. Find the rate of change of the radius when the radius is 2 inches. Okay, so let's picture this. If I had a balloon, I would blow it up here. And notice they tell you this is a spherical balloon. Most balloons are not perfectly spherical, but for us to be able to do this, we need it to be perfectly spherical, right? We got to simplify it a little bit. But if you are blowing up a balloon, if you picture in your mind, pretty much everybody hopefully has blown up a balloon before. Like if you think of, most of the time you're probably not blowing up the balloon with with an air pump. You might be, I don't know. But you're blowing it up like with your breath, right? So if you think of maybe like each breath being like that constant rate, like you've got one, you could kind of track it, 1 breath, 2 breaths, 3 breaths. They might not all be the same, but they could be close. At first, whenever you blow up that balloon, it's going to go from flat, it's about this big, right? And then you give it another breath and it might be this big. But what happens there towards the end whenever it's almost full? It's getting just a little tiny bit bigger each time, right? You're putting the same amount of air into the balloon, but its radius is not growing as quickly. And this is sort of, I realize blowing up balloons for a birthday party, you're not going to be analyzing this, but certainly you can see like this is actually what's happening for this. At first, the radius is going to change quickly, but then it's going to kind of slow down after that. Air is being pumped into this balloon at a rate of 4.5 cubic inches per minute. And then we got the rate of change of what we're looking for, the rate of change of the radius when the radius is 2 inches. So let's think about, first of all, what formula we need to be talking about for this balloon. What are we looking at the balloon, for the balloon? We're talking about air being pumped in. It's volume, right? We need volume, and this is a spherical balloon, so we're going to use volume of a sphere. And so most of the time when I see these, they give you the formula in the problem. If you see anything in your book where it does not give you the formula in the problem, I believe it's either the front or the back cover of your book has all those formulas that you'll need if you need to look something up. But volume of a sphere is 4/3 pi r cubed. And make sure you cube that because volume is cubic, right? A lot of times students get them wrong because they use a square on that there. So that's our volume of a sphere. Okay, we're going to need to take the derivative of that. So when we take the derivative of that, derivative of v is going to be dv dt. Okay, just like the last problem, 4/3 pi is a coefficient, right? If we could type that into the calculator, we could get a decimal for it. So when we take the derivative of this, it's just a simple power rule. So we are multiplying 4/3 pi times 3. And when we do that, 4/3 times pi times 3, this is over 1, this is over 1, that 3 cancels with that 3. We're just going to get 4 pi. And then we subtract 1 from our variable, so we get r squared. And I just took the derivative of an r, which means I need a dr dt with that. Okay, so this dv dt and the dr dt, those are rates. So dv dt is the rate at which the volume is changing. Dr dt is the rate at which the radius is changing. So what are we looking for this problem? What variable are we trying to solve for? Dr dt, because it says find the rate of change of the radius. Rate of change of the radius is dr dt. So right here is what we're looking for, dr dt. We are not going to replace that with any numbers. Okay, which means we need to be able to replace dv, dt, and the r right here. Those are the other variables in the problem. Troy, what is our dv, dt? What? 4.5 cubic inches. Perfect. That is the rate at which our volume is changing, right? That air being pumped in. It doesn't say anything about volume there, but it's cubic inches, which tells me it's volume, right? So that's the rate the air is being pumped in. That's our volume changing. So 4.5 equals 4 pi. And Abby, what would our radius be? 2 inches. So we put 2 right here. And then we leave that dr dt alone because that's what we're solving for. So we got 4.5 equals, we need to square that 2 first, which is going to be a 4, and then we'll multiply it by the 4 here, so we'll get 16 pi dr dt. And we're trying to get that dr dt by itself, so we'll divide both sides by 16 pi. And I don't like having decimals and pies, and I'm just gonna go with decimals on this. We get, if they wanted it to be a calculator inactive problem, they probably wouldn't give you 4.5 for that. They'd probably just give you like 4. So we get, if we divide that in the calculator, I'm getting oh wait, hold on, I might not have done that right. 4.5 divided by 16 pi. Oh yeah, I didn't do it right. Try that again. 0.089524 is my dr dt. We need to always put units with this. Liam, what would our units be? Mm-hmm. So it's dr, huh? Nope. Nope. All right, so look at the variable that we're using. Dr dt is the rate of change of r with respect to t. What do we measure r in? R is radius. What do we measure it in? Inches. What do we measure t in? What do we measure time in? Minutes. Right, for this. So it is inches per minute. And you can round that to 3 places if you want. This is an instance where I prefer to just keep a lot of decimal places, because that 5 is going to round that 9 up to a 10, and then that makes that a 9, so it'd be 0.090 if you want to round it to 3 decimal places. If I find myself having to do that, I usually just keep extra decimals so that I don't have to do that. It's a slightly tricky rounding. No sense in risking a point off of that rounding. I would just keep more decimal places. Okay, notice that number is really small. If I had plugged in, for example, like 1/2, I would get a bigger number. If I plugged in a bigger number, like 6, right, I'd get an even smaller number. Think about whenever you're blowing up a balloon, those last few breaths, the balloon's just barely getting bigger. You're just kind of like, it stretches just a little bit more, about ready to pop, right? That's what you're looking at here. Again, I don't think anybody's going to be using this to analyze something where they are, whenever they're blowing up balloons at a birthday party. But really, it's Math 3 where that could be.
Because we were talking about a
Yeah, it was, what were we doing? I think you were just talking about senior prank and I went down that road. It wasn't in your curriculum. Math 3, Mike could do it, because volume is in their curriculum. Yeah, because we were talking about, like, how it seems cool, but actually doing it would be way more time consuming and costly than you would think. But I would like to try it, but it's not really in our curriculum, unless I might can figure something out. We do have some time after the exam. We might have to think about it. Okay. All right. Now, this problem I really like, because this problem, ripples in the pond, like, I get what's happening there, and I get how, like, I'm not certain, because certainly I'm not an oceanographer, and I think the depth of the water matters and stuff, but, like, I feel like that ripples in the pond question could probably apply to some, like tidal wave sort of scenarios, possibly, you know, where you might could look at that. Not certain about that. I think it's probably more complicated than just that, but definitely if you have a underground earthquake in the ocean, it's going to spread out like that. I'm just not exactly sure what all factors have to be considered. The balloon problem. I think there are probably some design scenarios where you might need to consider it for, you know, if you had like a robot that was supposed to somehow like blow up something and you needed precise measurements on things. Maybe. I could see it. This one, I think makes so much sense to me about, now definitely if you just work in this building, you probably don't know how to do it. But if you're the one that designs this apparatus, you probably know about these things. So I really like this problem. An airplane is flying on a flight path that will take it directly over a radar tracking station, as shown. If S is decreasing at a rate of 400 miles per hour, when S equals 10 miles, what is the speed of the plane? So, again, I am not an expert on radar, and I am sure that if you work in this building looking at radar, that the computer does a lot of it for you. You don't have to be able to do these calculations. However, it makes perfect sense to me that that radar is sending out waves to this plane. And those waves, it's able to measure this distance right here, right? Maybe an angle as well. I'm not sure. We don't need an angle for this problem, but it's able to measure this distance. However, it's not measuring this like vertical distance or this horizontal distance. It's measuring that combined distance right there, right? So the information that it is getting, I would think, would be the rate at which this S right here is changing, right? It's getting that distance that you are from this. So if you know the rate that this S is changing, you need to also know, like, that's not the rate that S is changing is not the speed of the plane, right? Because this plane is not dive bombing into the building right here, right? The plane is just going over the building. It's keeping a constant altitude. So as this equipment measures this angle, right, or measures this value right here, some math has to be done to give you the speed of the plane, right? So looking at that picture, this is different because this is not an area or a volume problem. What formula do you think we are going to start with? Pythagorean theorem, exactly. Now, is 6 changing that height? No, it's not in this particular case. Now, it could, right? That plane could have a changing altitude, and if it did, then we'd have to put a variable there for that 6, which would make the situation more complicated. You'd have to have more information. But we know for this particular plane that it is flying directly over at a constant altitude. So we are going to say x squared plus 6 squared equals s squared. And we can plug in 6 because it is a constant number that is not changing in this equation. However, x and s are both changing, so we can't plug in numbers for those. So we're going to take the derivative of this, and we'll get 2x dx dt. This is 36. What's the derivative of 36? 0. So it's going to go away. And then we'll get 2s ds dt. Right here. And so now we've got to plug in some numbers. We've got to think about what we're looking for. What value are we looking for? What variable are we trying to solve for? Dx dt. It is not s because s is not speed in this case. The x dt, because the rate at which x is changing here is going to be the speed of that plane, because that plane is going in the direction of x right here. So the rate at which x is changing is your speed for the plane. Actually, dx dt is not actually your speed. What is dx dt? It's really close to speed. It's going to be velocity. So this is going to be your velocity here. But if we know velocity, we just know speed is the absolute value of that, right? So if we find velocity, we can find speed. So really, this right here is going to give us velocity. Sometimes it might ask for velocity where you want that sign. This one wants just speed. So if we get a negative, we're just going to say a positive for our answer. All right, so that means we got to plug in everything else besides this. It is telling us here s is decreasing at a rate of 400. Which variable is that? ds dt. And since it's decreasing, should we plug in 400 or negative 400, right? Okay, so then it gives us, it's pretty clear right here, right? S equals 10 miles, so S equals 10. That one's pretty easy to find. We have one more variable over here. We got an x. X is not given, right? Perfect. X squared plus 36 equals 10 squared. Now we can't plug that in before we take the derivative because s is changing, right? But we can go back to the original to find what x would be whenever s is 10. So that's going to give us x squared plus 36 equals 100. We're going to subtract that 36. X squared is going to give us 64. So x is going to equal, technically it's plus or minus 8, but in this case we know positive 8 is the only one that's going to make sense. So we got 2 times 8 times, we don't know dx dt. That's what we want to find. Equals 2 times negative 400 times ds dt, which is, oh wait, I put that in the wrong spot, didn't I? The s is 10, and the s dt is negative 400. So we've got 16 dx dt equals, this is going to be negative 8,000. And we will divide by 16. So dx dt is going to give us 500. Yeah, negative 500. That negative velocity is because we're going in the negative direction. Right there, we're going, that distance for x is decreasing. However, it asks us about speed, so we're just going to do a positive 500 because the direction is not important. And we need to know the units for this. So again, we're doing dx, dt. So we're thinking about what x is measured in. What is x measured in? Miles. And what is t measured in? Hours. So this would be 500 miles per hour. Now, I am pretty sure, I do not have any direct experience with radar. I am pretty sure that if you're sitting in that building, that your computer screen is probably telling you that the plane's going 500 miles per hour, that you're not calculating this. However, the super duper smart people that created radar and set up the machines and hooked it to the computer program and programmed all the things so that you could see on the screen what is happening, I'm pretty sure they have to know how to do this, how to set that up so that the computer can calculate things. So I always tell students that if you have a job where you're really doing calculus every day, in your job, you're either a math teacher or you have probably a very high-paying job somewhere doing important stuff for like crazy stuff. I always would love to have somebody like come in and talk to us that did something like this. The problem is I don't know anybody that has a job like this. If you guys run into anybody that has, like, does some calculus in their job, please let me know. I'd love to talk to them and see if they'd come tell us all about it. But I'm pretty sure we need, like, somebody from the Pentagon to come tell us about these sort of things. And I don't have a lot of connections there, unfortunately. So, all right. Okay, so assignment for this is page 194, 14, 15, 22, 25, 26. For that. And let me double check, make sure those look good. Okay, yeah, all these are good. 22 does have a picture that goes with it, but it's down below 21. If you see that picture, it will help you a lot to know what to do with that. So 22 does have a picture with it. So we got about 20 minutes for you guys to work on this. So go ahead and get started. You're welcome to work together. You can do whiteboard if you want.